our final piece. We are looking at independent samples today. So yesterday we were talking about when we were doing hypothesis testing with two different groups, but they were related somehow. What kind of data did we have yesterday? Matched pairs. There was a connection. It wasn't just two random sets. It was one person's test score in two different classes, or like the ring. I don't remember. We had a hotel price for two different hotels, but in the same city. So somehow the data was connected. We also need to be able to compare truly different sets of data where they are not matched up in any way, shape, or form. The calculation is a little more complex for this one. So if you are looking at the formulas, it's pretty nasty looking. Again, we will mostly do this on the calculator. I think I may work one out by hand just to kind of show you how to make sense of this formula, because that is beneficial to be able to read a formula and plug in things appropriately. But as far as when it comes time to set you on it, I will be having you do these tests on the calculator just because it is a lot of data grouped together. So, the t-value here, it's called the Welch's t, it kind of explodes. We're used to doing a normal t calculation, which is our value minus the mean divided by standard deviation, essentially, right? Like a z-score. This is similar, but what do you think the x bar 1 and x bar 2 mean? Yeah. It's our mean from two different sets of data. So that's our value minus the mean of each original set of data divided by, what do you think these s sub 1s and n sub 1s, standard deviation and number for each of the different sets. So it's a similar calculation. We're used to doing x bar minus mu divided by the square root of s over n. But because we have an x bar for each of the two data sets, a mean for each of the two data sets, standard deviation, and n, the formula kind of gets a little bit nasty here. Criteria, anytime we're dealing with the mean, our main criteria that we've been checking is either that the set is normal or that we have at least 30, and that is still the case here. The other things we are kind of assuming random sampling, independent, less than 5% of the total population, so we're kind of just assuming that part. But when I ask you to verify criteria, just like any other time we're talking about the mean, you need to tell me either it has to be normal or, in this case, both data sets have to be bigger than 30. Since it's not matched pairs, there might be different numbers of points in the sets. So both of them have to be bigger than 30. Okay. So our hypothesis testing. We know the null hypothesis is always equal to. Yesterday we were looking at the mean of the difference so that we could take our two sets of data and put them together because they were matched pairs. Because these data are not paired up, we can't look at the difference. It wouldn't be meaningful. So the null is going to be that the two means are equal. So the mean of the first set equals the mean of the second set. And then the alternative would be less than, greater than, or not equal to for each of them. So we'll make our null and alternative hypothesis. We'll have to find our alpha level, get our t-value, and then we have the classical or t-value or p-value approach. Classical approach is using the t statistic from our table and seeing if we're in that shaded region. P-value is what we've been doing mostly because on the calculator it gives us the probability. So then we just have to verify that the p is, see if the p is less than alpha. So let's work through one. And we're essentially just going to do one problem today, but I'm going to do it several different ways. I'm going to show you how to do it by hand. I'm going to show you how to do it on the calculator. We'll look at how to do it with confidence interval. So because there's so many points, I didn't want to just do a different set of points every time. We're just going to take this one set and look at it. So a researcher wanted to know whether state quarters had a weight that is more than traditional quarters. He randomly selected 18 state quarters and 16 traditional quarters, weighed each of them, and obtained the following data. Test the claim that state quarters have a mean that is more than traditional at the alpha equals 0.05 level. So what is my null hypothesis here? Okay, mean of the first equals mean of the second. We are going to treat the state as the first group and the traditional as our second group here. Then the alternative. We want to see if the state has a mean that is more. So what would my alternative be? Mean of the first is greater than mean of the second. All right. In this, I should have stated in my problem, I'm going to tell you the original data is normal. Kind of like yesterday, most of the time I'm not going to give you over 30 points just because for the sake of time. So for today, I'm giving you data that is already normal, so our criteria will be met. Should have stated that here. Okay, so now what I want you to do, enter the state in L1 and your traditional in L2. Could this be matched pairs data? No. What are some big indicators that it's not? Yeah, we don't even have the same number of points in both, so it would be impossible to be. If I were looking for matched pairs, is there any way I could link a state quarter to a traditional quarter and say they're related in some way? No. So it wouldn't even make sense to try to set this up for matched pairs. All right. You want to do it by hand first?
Yeah.
That would be fun. We should do that.
I don't know what your definition of fun is.
Math. All right. So if we were going to do this by hand, and I think, did I leave you guys some empty slides there? Okay. We need some information from these. If you think about the t that we have to calculate, we need the mean of each set, standard deviation of each set, the number of each set. So where can I go to get all of that information? Stat, calculate. Yeah, we could do two variable statistics. Just make our x L1, the y L2. Oh, it's not going to let us though because they don't have the same number. So we'll just have to do one at a time. So one variable statistics, let's do L1 first. Okay, so the mean of my first set so this is for my state quarters. Mean 5.7022. Standard deviation is 0.0497. And the number 18. Okay, if we did it for the traditional, and so this time I'm doing my one variable statistics for L2. So the mean of this set, I'm going to call the first one's my state. I'll put a subscript of 1 on all those, my traditional, my second set. The mean was 5.6494. Standard deviation 0.0689, and the number in this sample was 16. All right. Did everybody get that? So let's look at our T formula, so you can use the notes, or if you're looking at your formula packet, the chapter 11, second column, it's the first thing there, your test statistic for computing two means independent sampling. So the T is x bar 1 minus x bar 2. Minus, okay, we have a problem. Mean of the first minus mean of the second. Did I tell you the mean of all state quarters and all traditional? No. But look at our null hypothesis. The null hypothesis is that those are equal. If they are equal, what do you get when you subtract them? 0. So because of my null hypothesis, I can say the null hypothesis is that they are the same. So in the formula you subtract them, we would get 0. Divided by the square root. Standard deviation of the first set. Divided by number of the first. Oops, oh, I've dropped off my square. Standard deviation of the second set squared. Divided by number of the second set. So now we put this in our calculator. Is it 2.53? So then, if we were to do the classical approach, just kind of refreshing, you guys like taking the time and going back to how we did things before, right? What we always did is drew a picture. Okay. Our degrees of freedom, when you have two different sets, your degrees of freedom we know is always n minus 1. It's based off the smaller. So one of these had 18, one of them had 16. So we have to go with the 16, subtract 1, so we have 15 degrees of freedom. And it told us in the problem that our alpha was 0.05. So if you go to your T distribution, the 0.05, 15 degrees of freedom, that means the critical value is 1.753. And so the classical approach says we reject anything that's in our shaded region. So the T we got was 2.53. So this will be over here. And so since our T is in the shaded region, we would reject the null hypothesis. Okay, if I ask for the p-value approach. So we have a lot of ways of doing these. We have to use our table to try to estimate our probability. The degrees of freedom is still 15. And the t that we calculated was 2.53. So you go to the 15 degrees of freedom row, you're going over to 2.53. Now we're very limited, so what's the closest we can get to 2.53? 2.602, and if you look up, that corresponds to a probability of 0.01. So we use the table, get a probability of 0.01. Compare that to alpha. So since p is less than alpha, we reject. So classical or p-value, we have to first calculate that t statistic, and then we can look at it just a couple different ways. Questions there? But it's kind of silly to do all this by hand when we already put the data in the calculator anyway to get our mean and standard deviation and all that. So it really just makes the most sense to do this test on the calculator. So I've shown you how to do it by hand. Now let's talk about if we just did it on the calculator. So at this point, we have everything entered in one in L1, one in L2. And then you are going to go to stat tests. Oh, I don't have it. Okay. So we know anytime we're talking about the mean, we do a t-test, right? But now I have two different samples, so we want number 4, a 2-sample t-test. Okay, and then it's going to ask us, is it based off data or stats? Data is if we have put everything in L1, L2. Stats is if we're reading the problem and it says the mean of this group is this, and the mean of this group is that, and standard deviation is this, and we have to fill that stuff in. So this is based off data. List 1 should be L1. List 2 should be L2. Both frequencies should be at 1. We were testing greater than. Pooled. Make sure that is set on no. So pooled should be no. And calculate. All right. So it gives us a lot of information. We've seen some of this before. The mean of the first, mean of the second, standard deviation of each. But what's really important, if I were asking you to show me work on this, I usually have you write down the t and the p value at this point. T 2.537, that's pretty close to what we calculated by hand. The p is 0.0086. And then what's my conclusion? Since p is less than alpha, we reject the null hypothesis. So that means we rejected the null, so there is evidence to conclude let's see, our alternative was that state quarters weighed more. So we have enough evidence to conclude the state quarters have a higher mean. I know I did a lot of work on that one. definitely more than you are required, just because I wanted to show you all the different options for figuring it out. But we got the same conclusion every way, whether we did it by hand, classical, p-value, or calculator. Any questions there? Last, we've also talked about using confidence intervals with these. So if I asked you to do a confidence interval, again, because we have two different means, the formula is a little bit uglier. It involves subtracting the means of each individual set, plus and minus the t value times the square root of standard deviations. So very similar to our other calculation. So let's make a 95% confidence interval for this. All right, you want to do it by hand and on the calculator? Compare?
No, it's up to you, an option.
Oh, I think we should. You want to practice some by hand, right? I don't want to deny you of that opportunity to feel the satisfaction in getting it on your own. Okay, so we already have the means, standard deviations, and ends from our other calculation. What we need is that T alpha over 2. So we have a 95% confidence interval. That means we want 95% of the data to fall in the middle. So how much is left for the ends? 5% total, so if you split that up over the two ends, that's 0.025. And we know then our degrees of freedom was still 15. So if you go to your T distribution, 0.025, 15 degrees of freedom, we get 2.131. So if we were doing it by hand, from either your formula sheet or that piece in your notes, we have to do the mean of the first minus the mean of the second. So the mean of our state quarters was 5.7022. The mean of the traditional quarters, 5.6494. I'm just going to go ahead and write plus and minus T alpha over 2, 2.131. The square root, standard deviation of the first one, squared, divided by n of the first, the standard deviation of the second one squared, divided by the number in the second. All right, let's see if we can type it in. So that's good practice for us. If we wanted to do it on the calculator. All right, we are looking for the confidence interval, so we go stat, tests. So normally we do a T interval, but what's different about this one? We have two different samples. So we have to go on down to 0. 2 sample T interval. Okay, ours is based off data because my stuff is entered in L1 and L2. Otherwise, you would do stats and put in all the numbers from your problem. So my list is L1, list 2, L2. Frequencies are 1. Confidence interval, I asked for a 95%. Pooled, always keep that set on no. It's like grouping the data together.
Don't want that.
And so we get 0.011 0.0956. Why are these not exactly the same?
Rounding error?
Rounding. When we are doing this, our calculator can do a much more accurate degrees of freedom calculation and t-value than we can get from our table. We're very limited. So it is important. You'll see we do have a little more error than we're used to on the confidence interval with this. So please, please, please make sure that I know how you're getting your answer if you're doing it on the calculator or by hand. Questions there? So I'm really done with section 10.3. You have, or 11.3. So you have your chapter 11 packet, and this is going to be due. I'm probably not going to collect this until, what's today? Today's Tuesday, so Thursday. So tomorrow you will have some work time, and I will also probably do some practice with you guys. I'm not teaching anything new, but we'll practice and have time to work. Did somebody take one of my calculators?
Yes, it was